Okay, so you just turned in homework number 3, and homework number 4 is due a week from today, but it's confined exclusively to things that we're covering today. So there's no reason to delay that assignment. In fact, it'll just get harder the longer you wait. The stuff we talk about today will be less fresh in your mind, and then in my past experience, sometimes students try to apply the techniques that we're going to be talking about on Friday and Monday on homework 4, and that's wrong. It's actually just exclusively related to today's stuff. And so let me show you the assignment. There's only 2 problems, but it's worth 70 points. So that should give you an idea that each one of those problems is a little bit above average in terms of the amount of time it's going to take for you to solve them. Let me just pull it up. Okay, so homework 4 is what you're working on. Due at 11 o'clock next Wednesday. And so both of these, you need to apply the Nodal method, which is what we're going to be talking about today. And homework problem number 1 is, there's a fair amount of calculations there, but it's not like conceptually very complicated or difficult. It's just there's a couple of pages of calculations for problem 1. And problem 2 is a little bit more of a brain buster, although that's giving it too much credit. It's not that complicated, really. You just have to kind of do like a step-by-step logical analysis. And the first part of being successful on problem 2 is reading and think about all the instructions before starting the problem. And the mistake I've noticed in the past is that students just start doing the calculations before bothering with all of the hints that I've given you. I've given you, this is what, maybe the 18th semester I've taught hydraulics, and I've assigned this problem a lot of times, and I've seen how some people crash and burn on this when, like in the past, it was just the image, the data, and calculate the flow through each pipe. So I've kind of looked at what mistakes people have made over the years and tried to steer you away from some of the most common mistakes with giving you some hints. So everything you need to know is in the handout, and I really think it would be wise to read and think about the suggestions I've given you before you start the calculations rather than just jumping right in. So the other thing I suggest is that it's normal for this to be several pages of hand calculations. Like my solution, I think, is 4 pages of hand calculations. So don't try and cram it into a single page using like extremely small writing. Paper's relatively inexpensive. Just let your work breathe, spread out. Give it enough room that you're able to be logical and clear in your presentation of the process. So hopefully that hasn't unnecessarily intimidated you with the assignment. I don't think it's likely to take you more than 2 or 3 hours. It's a lot of writing, a lot of algebra, and a little bit of logical analysis. Okay, so that's all I want to say about homework number 4. And then on Friday and Monday of next week, it's really important that you have a laptop with you because we're going to be using Excel extensively for the next couple of days. So any questions before we move on? At the beginning of class last time, I asked you what's the fully turbulent flow assumption, and I was a little bit sad that nobody could answer that question. So I don't want to disappoint myself again, so I'm not going to ask. I'll just give you a refresher. The fully turbulent flow assumption is just built on the understanding that if you have really high flow rates through a pipe, then the Reynolds number is going to be high. And there's a certain portion of the Moody diagram where the Reynolds number only depends on the relative roughness. So look, see how this is really flat, this part of the Moody diagram? What it means is that you'd get the same F value whether you had a Reynolds number of 10 to the 6th or 10 to the 7th or 10 to the 8th. It just means that there's a certain velocity where beyond that, the F value isn't changing anymore. So in that fully turbulent flow range, it's only the relative roughness that dictates the F value. So this is just a technique we can use to start with a better guess for the F value than picking a number out of thin air. If you assume the fully turbulent flow assumption, then what you're doing is you're taking the Jane equation and you're removing this Reynolds number term from it, because what you're saying is that if the velocity is high and the Reynolds number is high, since this is in the denominator, then it becomes negligible. So we can estimate the F value just by taking into account the relative roughness component of the Jane equation. Or, if we were thinking in terms of the Colebrook equation, again, it has both a relative roughness term inside the logarithm and a Reynolds number term. And if RE is very big, then it makes the second term negligible, and then F is just a function of the relative roughness. So you can't always just calculate F with this. This is just like a first draft estimate of F. And so if you assume the fully turbulent flow assumption, then at the end of your calculations, you need to verify whether or not that assumption is true. Sometimes it will be true, and if you calculated a new F value with the full version of the Jane equation, then you'd get the same thing as your first time around, in which case you can stop your calculations. But there are going to be other cases where you assumed fully turbulent flow. It turns out that actually no, the flow wasn't fully turbulent, and then you're going to have to adjust your F value in the second and subsequent iterations. So we've done that before, the idea of just continuing to calculate over and over again until the solution converges. It's just your solution will converge more quickly if you start with a reasonable guess of F. And the fully turbulent flow assumption is one way to do that. Any questions? Okay, so now let's talk about the Nodal method. This is the heart of today's today's lecture and your next homework assignment, homework 4. It's an application of the continuity principle. And the continuity principle is the same one that I invoked when I was talking about flow into a pump. Remember in our last class period, what I said is that a pump adds energy, and the way that it adds energy is through an increase in pressure. Because if we have water flowing through a pump, and the diameter of the pipe is the same, then the velocity in and the velocity out are the same, because the flow rate in and the flow rate out is the same. So continuity principle says, let's put like a little imaginary box through some zone that we're interested in and keep track of the inflows and the outflows. So you've seen continuity principle before. We're just going to apply the continuity principle in different ways today. What we're saying is that we're going to look at a pipe junction where two pipes come together and one pipe goes out, and we're going to analyze the flow in and the flow out of the junction. And what we know is that if it's just pipes welded together or bolted together and there's no reservoir, then there isn't any capacity for storage. And if there's no storage capacity, then the flow in and the flow out have to be equal, because liquids like water are effectively incompressible. We can compress them a little bit. And we'll talk about that this semester when we discuss water hammer. But it's pretty infrequent that the compressibility of water is an issue. So continuity just says inflow equals outflow. So here you can see that the flow rate through pipe Q is equal to the flow rate through pipe X and the flow rate through pipe Y. Flow in equals flow out. So we just put a control surface around some location where things are happening, and we go into accountant mode and keep track of in and out. So the application for this Nodal method in like municipal pipelines is situations where flow splits. And this is pretty common to provide redundancy, because if there is a rupture in a pipe and you need to close off a section of it, it's best if the water can get to different parts of the network through a variety of routes. And it also helps to avoid things like the pipes getting clogged because there are dead ends in the pipe, and sometimes minerals like manganese and iron and so on will precipitate out. So look at this. This is like a top view map. We're looking down from above where there's a big pipe that splits into two smaller pipes, and it comes back together again. So if we know the flow rate through the single pipe, then what the nodal method is going to allow us to do is express the flow in either of these other pipes in terms of the known flow rate and the other pipe. So, for example, if we wanted to express the flow rate through pipe B, we could say it's the known flow rate, pipe A, minus however much is going through C. And so think about, does that make logical sense to you that the flow rate through B is however much is in A minus the amount that's going through C? Because in this figure, QC plus QB equals QA. So another way to express these flow rates in terms of each other is just that the flow rate through QC is however much there is in the single pipe minus the amount that's going through the other split pipe, pipe B. Okay, it's hard to know so far how this is going to be such a powerful tool, but we will get there. Before we do, anybody been to Winter Place before? A couple of people have been to Winter Place. They're liars, by the way. I looked on their website today. I was interested what their vert is, you know, like from the top of the mountain to the bottom of the hill. They say it's 603 feet. It's not. I looked it up on Google Earth because I was curious to know, like, how much is it really? They claim that their mountain goes up to 3,600 feet. According to Google Earth, it only goes up to 3,554. And then they claim that the bottom of their lift is at like 2997 or something, and like even if you ski right next to the parking lot, I don't think it goes that low. So anyways, they're claiming that they have like 603 feet of vertical elevation, and more is better. When it comes to skiing, you want tall mountains because then it means that you can ski a lot with each run. In contrast to one of the most recent places that I've skied is over in Dubai, which is in the desert. You know, they have an indoor ski resort at one of the malls there. The Mall of the Emirates has an indoor ski resort. And I think from the top to the bottom, like in terms of vertical drop, it's maybe 150 feet. I mean, it's fun. You know, you can do the run in about 90 seconds. So, you know, in a given day, you'd go up and down the mountain dozens of times. But when it comes to skiing outside of the desert, taller mountains are better. Obviously, they're bigger. But they're better because, you know, you want to get speed, you want to have length of time going down the run. But here's where it comes into the nodal method. If we go from the top of the mountain to this lowest point that's skiable, then it doesn't matter what route you take. The elevation change is the same. So, for example, if I am a real daredevil and I'm going to go down these black diamonds, nose dive. So if I go down the black diamond from the top of the mountain, I go on nose dive, and then I guess from there I'm going to have to take some pretty easy runs. Country road, then over here to the ski school area. I end up at 3,062 feet. So if I did that, if I'm starting in the same place and ending in the same place, the vertical change is the same as if I went on Ridge Runner and Meadows and Last Chance and so on. So the elevation change is the same regardless of the route that you take. So they all have different ride characteristics, and so you're going to go faster on nose dive than you are on Woods Run because although it's the same elevation change, Woods Run has a longer length. And the slope is the change in elevation divided by length. So the steeper the slope, the faster it's going to be on your skis, and the harder you're going to hit the ground when you fall off, if you're moving really fast. So Woods Run has a longer length, even though the delta Z is the same. for plunge versus Woods Run. The delta Z is the same. Since Woods Run has a longer length, the slope is less. But the key analogy I want to make here is thinking about an elevation change. It's the same when you have a starting point and an ending point. So back to hydraulics. If we have this junction where pipe A branches into pipe C and pipe B, if we're at that junction, then there's going to be the same amount of energy loss if we go through pipe B or pipe C, because they're going to come back together again, and so the amount of head where the two come back together has to be the same. So let's do a series of hypotheticals here. Let's just say, what if that pipe B and pipe C had the same length? So there's nothing different about them in terms of the pipe length. What if they had the same diameter? They're made out of the same pipe material. Then what would be the split in flows between pipe B and pipe C? How much would be going in each?
Half and half.
It'd be half and half. Exactly right. There wouldn't be any reason for it to be anything other than half and half. Like, if the pipes are identical, then why would water prefer to go through one versus the other? It wouldn't. Now, water's not making conscious choices. It's not a matter of preference. But I guess what we could say, to put it in more scientific terms, is that there wouldn't be any reason for an equilibrium other than half the flow going through pipe B and half the flow going through pipe C. Okay, so here's another hypothetical. What if they have the same diameter and the same length, but what if pipe B is more rough? Which of them would you expect to carry more water? Pipe C. If pipe C is more smooth, what we know is that higher flow rates can go through pipes that are more smooth. So how much would go through pipe C versus pipe B? The flow rate equilibrium would be whatever it takes, whatever flow rate it takes for there to be the same amount of energy loss through both pipes. So that is what would dictate how much goes through B versus how much goes through C. And so if C is more smooth, then it's going to take more flow through the smooth pipe to achieve the same amount of head loss as compared to pipe B. Okay, what if the diameter of pipe C is bigger? Same material, same length. So which pipe would carry more flow?
C.
C makes sense because it's a bigger pipe. It can accommodate more flow. Now, there are times where it's not going to be exactly clear. So this one, what if the diameter of B is bigger, but then it also has the longer length, and then pipe C is more rough? So like this one, we're not going to just be able to know from the qualitative description we've got, because we don't know how much bigger and how much longer. But like, since pipe B in this next example has a larger diameter, that would start us off in thinking maybe more flow goes through B. But then if it's longer, it's going to encounter more friction losses because of its length. So now we're conflicted because we don't know which of those two effects, its added length or its larger diameter, is like the definitive thing that's controlling. And then to muddy the waters even further, pipe C is more rough. So we don't know what the flow rate would be in that, but we could calculate it. And the approach that we're going to use to calculate the distribution in flows is just this knowledge that the head loss through each pipe is equal. That it doesn't matter if we go through one route or from the other route, that the amount of energy loss is the same when you have the same starting point and the same ending point. So just like with the mountain, it doesn't matter which route you go through, the amount of energy that you've got when you're standing at the top of the mountain, potential energy, and the amount of energy you've got when you're standing at the bottom of the mountain, like represented as your elevation, the change in energy is the same regardless of which route you went to get there. So that is true in hydraulics as well. So if we can estimate the head loss through a pipe using Darcy-Weisbach equation, then what that tells us is that for each term of Darcy-Weisbach equation, the F value, the length, the velocity, the diameter, well, G is a constant, but for each of these other terms, it could be unique parameters through each pipe that the head loss is the same, pipe B versus pipe C. So we can find out the two things that we would add together to solve the distribution of flow rates is, number one, the continuity principle, and number two, this idea that the head losses are the same regardless of whether we go through pipe B or through pipe C. So does everybody see that idea that the amount of energy where they come back together again, like this junction, the junction where they come back together again, you couldn't have a different amount of energy at the end of pipe B versus pipe C. They have to have the same amount of energy because they're coming back together again and forming a single pipe. So they'll have ultimately the same amount of head, which means that the head loss through each route has to be the same. So does anybody have any questions so far? Okay. Junction 1 is where the pipes split. Junction 2 is where the pipes come back together. And it doesn't matter whether you go through pipe B or pipe C from 1 to 2. But regardless of the route, the head loss is the same. So think about the energy equation. Here's the energy equation. Pressure head, elevation head, velocity head, plus the pump head that's added between point 1 and 2 is equal to the pressure, elevation, and velocity head plus the losses that occur from pipe friction and local losses. So the head, when we talk about how much energy is there at 1, what I mean by head is if you add together the three terms that encompass how much energy there is. And it's just expressing energy in units of length. So meters or feet. So it's the pressure divided by the unit weight of the fluid plus the elevation plus V squared divided by 2G. All three of those terms have units of length. We add them together. And what we're saying is that the head at 1 minus the losses through either of the pipes is equal to the head at 2. This is the energy equation. You probably wouldn't recognize it as the energy equation, but it is. That's just the energy equation, which we've rearranged a little bit. So H, I told you here, H is pressure head, elevation head, and velocity head. So here, this is just saying the total energy at 2, that's the downstream location. So the energy at 2 is however much energy there was at 1 minus the losses plus the pump head. So in words, that seems simple enough. I'm telling you, the way that you describe this in text is the energy at 1, or the head at 1. The head at 2 is equal to the head at 1 minus, here's the friction losses, FL divided by D. That's related to the friction component. And we know that the sum of K naught, that's talking about local losses. So if we add up FL divided by D and the friction losses, then we can multiply that by the velocity head, because both the Darcy-Weisbach equation is H sub F is FLV squared divided by D2G. So if we just say, well, let's group that together, and head loss due to local loss is the sum of K times V squared divided by 2G. So we'll take that. It's both of them is the velocity head, V squared divided by 2G. So you could combine FL divided by D and the sum of the local losses. So that's why we've got these in a parentheses. It's just, we're multiplying them by a common factor, meaning the velocity head. Now, what is going on with Q and A? Well, I think I've already touched on this in a prior class. I've told you that there are situations where we don't necessarily know the velocity through a pipe, but we do know the flow rate. You know, like in design, where we haven't yet decided what the diameter of the pipe is, we don't necessarily know what the velocity is until we have selected a diameter. But even before we select the diameter, we do know the flow rate that needs to be carried through the pipe. So HF equals FLV squared divided by D2G, or another way to say that is FLQ squared divided by D2GA squared, because V equals Q divided by A. Okay, so you've seen this before where I said, instead of saying velocity, let's just say Q squared divided by A squared instead of having V squared. That's a substitution that I think is obvious enough. Now here, why we've got Q times the absolute value of Q is that sometimes in a system, we don't know what direction the water is going. We don't know if it's going, if it's like a looped network. We don't know if it's going clockwise or if it's going counterclockwise. So flow rate can have direction depending on what we assume to begin with. Like if we assume that clockwise in a pipe network is positive, and then counterclockwise we're going to assign a negative value, you'll just have to take it on faith for now that sometimes we want to maintain the directionality of flow. And so that's why I'm doing this Q divided by the absolute value of Q. Is there's going to be future times we use this equation where if all we did was just square Q, then the negative flow rate, like if you square a negative number, then the minus sign goes away. But here, if you have Q times the absolute value of Q, that preserves the sign. It preserves the directionality, but at the same time you're squaring it effectively to get the velocity head. And same thing here with the pump term. Q divided by the absolute value of Q, all that does is seeks to make corrections that may be necessary if you've assumed the wrong direction for flow. So what's this equation? It's the energy equation. It's just kind of, we've rearranged it for our purposes. But for the nodal method, this can be a useful way to calculate the change in energy between 2 points using the nodal method. So here's all the definition of the terms. The thing that's really important to emphasize is that location 1 is where the water flows from, so it's at the upstream end of a pipe, and location 2 is at the downstream end of a pipe. So 1 and 2 have directional significance. Okay, so let's try this with an example. Let's figure out for this flow network where we've got 3 cubic meters per second going through pipe A, and then the pipe splits. We want to know how much flow is going through pipe B versus how much flow is going through pipe C. And then also, we could, using this method, find out what is the pressure at junction 2 where the pipes come back together. So if we wanted to do that, if we wanted to solve a problem like this, then our process is going to find out how much head is there to begin at the upstream junction. So find the total head at 1 by adding together the pressure head, the elevation head, and the velocity head. And then you'd find the head at 2 in terms of the unknown flow rate through B, find the head at 2 through the unknown flow rate through C, and then set them equal to each other by equating the flow rate through B in terms of the flow rate through C. Because the 2 equations that we're going to use is continuity, the fact that the total flow has to equal 3 cubic meters per second. That's continuity. And then the knowledge that the head loss through B will be equal to the head loss through C. And so we could then find out how much head there is downstream at 2 by subtracting out the losses that there are from the original head that existed at 1. Okay, so let's work this example. You can see I've given you some things here off to the right. I've given you the reminder that the head loss through pipe 2 is the same as the head loss through pipe 3. We know that the starting pressure here at junction A is 900 kilopascals. We've got the pipe lengths. We know that everywhere is galvanized iron pipe, so we could use that to estimate our F values initially. You know, we can actually find out the relative flow rate through pipe 2 versus through pipe 3 even before finding out what's the head at B. You know, we can find out the relative proportion of the flow rates through each of them without having to know the flow through B. But let me suggest, first of all, let's assume fully turbulent flow. So calculate the F value that should be used for pipe 2 and the F value that should be used for pipe 3. So here is the abbreviated Jane equation for the fully turbulent flow assumption. Estimate the F through pipe 2 and the F through pipe 3. And then once you've done that, we'll continue the calculations together. Okay, so if you apply the fully turbulent flow assumption and you're trying to calculate the F value for pipe 2 and the F value for pipe 3, here's what you end up with. You know, you're substituting in the relative roughness into the abbreviated Jane equation where we've taken out the Reynolds number component of it, and you get 0.01493 for F2 and 0.01567 for pipe 3. So we need those because we're going to put them into this expression over on the whiteboard that the head loss through pipe 2 is equal to the head loss through pipe 3. So that's the governing idea of our problem solving strategy, is just knowing that the amount of energy that's lost through each of the pipes is equal. So if the head loss is the same through each pipe, then here's us setting the Darcy-Weisbach equation for pipe 2 equal to the Darcy-Weisbach equation through pipe 3, and then rearranging that just so that we've got the velocity of one of the pipes in terms of the velocity through the other. So this is just, you know, rearranging and isolating V2 in terms of V3. So what we get then, substituting it in, is that the velocity through pipe 2 is 1.204 times the velocity through pipe 3. So the velocity in pipe 2 is faster than the velocity in pipe 3. And since, you know, in the given data we knew the diameters and the pipe areas, that was given. So the velocity in pipe 2 is faster. Now, here's the continuity relationship. The continuity relationship says the flow rate through pipe 2, so Q2 is equal to Q2 plus Q3 is equal to 3 cubic meters per second. So that's, you know, the upper pipe plus the lower pipe is equal to 3 cubic meters per second, because, let me draw it on the whiteboard here. They come together, and what goes out is 3.0 cubic meters per second. Here's Q2, here's Q3. So together they equal 3. And this Q2 is A2 times V2, and Q3 is A3 times V3. So A2 V2 plus A3 V3 is equal to 3 cubic meters per second. And we know the areas. Those are like numbers that we can look up, which are calculated based on the diameter. So this is known. So it initially looks like we've got one equation and two unknowns, but actually we've only got one unknown because we've got another equation we can use. And that is this thing that we just barely calculated, that, you know, V2 in terms of V3. So what we could say is A2 times 1.204 V3. So I made that substitution, plus A3 V3 is equal to 3 cubic meters per second. So now we've only got one unknown because A2 and A3 are numbers, and so the only unknown is V3. So that's what we do here for the rest of it, is I put in the actual number for the area at 2, the actual number for the area at 3, and then I substitute in the velocity in 3 where we normally would express it as V2. So 1.204 times V3. So if we do that, then we're going to be able to get the velocity at 3 as 8.29 meters per second. And then if we substitute it back into our ratio of velocities, that tells us it's 9.98 meters per second. And just to double check to make sure it all fits together, by putting it into, like, calculating what's the flow rate through pipe 2, what's the flow rate through pipe 3, it adds up to the 3 cubic meters per second that we know it ought to. The only difference here, where it's saying 3.001, it's just a negligible amount of round-off error associated with the round-off of the areas and the velocities. So the double check verifies everything is good. The flow rates can be determined because we knew the ratio of the velocities. And, you know, I solved this one in terms of velocities. We could have also solved it in terms of the flow rate. So I could have written it like this. I could have said F2, L2, Q2 squared divided by D2, 2G, A2 is equal to F3, L3, Q3 squared divided by D3, 2G, A3. You know, that might have been even easier if we did it that way. It would have been easier because then, you know, we would have gotten Q2 in terms of Q3, and I don't know, it would have saved us this step here where we were having to calculate the flow rates from the areas. That's just, it's the same thing. It's the same approach where you're getting one flow rate in terms of the other. So are we done? No. Since we use the fully turbulent flow assumption, we have to check to see if it's valid. It may not be. So anytime you use the fully turbulent flow assumption, you have to check it. Check the validity of the fully turbulent flow assumption. So what that means is, now we've got velocities. Let's actually find out, using the full version of the chain equation, what's the F value. So let me just demonstrate that for you. I used the Reynolds number for pipe 2 and pipe 3, and I calculated a new F value using the full version of the chain equation. So the new F value is 0.01498. And what was our original guess for the F value through pipe 2? 0.01493. 1493 versus 1498. That's pretty close. So I think we're good with pipe 2. The fully turbulent flow assumption is valid because, like, if it's 1% difference, then there wouldn't be any reason of reiterating another calculation step. And how different is this? 0.01498 versus 0.01493 divided by 0.01498 times 100. It's 0.3% different. So that's below the 1% threshold. So fully turbulent flow assumption is valid for pipe 2. Okay, what about pipe 3? When we calculate the full version of the Jane equation, then the F value is 1592 versus our original assumption was 1567. Well, let's check that again. 1567, 1592. 1.6%. I guess if we were being really meticulous, then we'd maybe do another iteration, but 1.57% is pretty close to 1%, so I mean that's probably okay, no need to iterate another time. But what if we wanted to know how much head is there at these different locations? So if we wanted to know the head at those locations, then what we do is we'd start off with how much head was there at A, and then with the given pipe characteristics between A and B, calculate the losses. So like here, we know the F value, that's a given. You could calculate how much head loss due to pipe friction, and then how much head is there at B. And then find the loss through here, the loss through each subsequent pipe would allow us to find out the pressure at D. So like if we were assuming it was all the elevations are the same, that would be relatively easy. But even if we know the different elevations between point A, B, C, and D, we could account for that by including it into the energy equation. Okay, so this is one of your homework problems. Instead of 2 pipes, there's 3. It doesn't make it really that much trickier. The same principle holds true, that if you've got a splitting network, when they come back together, the head is the same at all 3 of the junctions. So the head loss through pipe 1 is equal to the head loss through pipe 2, and that's equal to the head loss through pipe 3. So you can use the same concept to find the overall flow rate is A1V1 plus A2V2, A3V3. You just need to solve for V2 in terms of V3, V1 in terms of V3, and then substitute it all into the continuity equation. So just a couple of hints on that first homework assignment here on this slide. And lots of hints on the second homework problem that are on the assignment page itself. You know, it's kind of a riddle, this second problem on the homework, and it's a riddle I want you to solve. So I'll tell you if you've got the right answer, but I don't want to give it away and short circuit that learning process. So if you have specific questions, feel free to stop by and I'll help you with it. But I'd be really reluctant to have you send me your homework and say, hey, where's my mistake? I'm not your homework checker. But if you've got a specific question, if you're doing something right, or if you want to know the final answer if you've got it, feel free to stop by and we'll definitely go over it together. All right, that's it for today. Remember that you need to bring your laptop on Friday. We're going to be using Excel.